morning. In this session we are going to discuss a lab work to create a mixture model using PyMC3. In the previous lab session we have seen how to use PyMC3 in probability distribution construction. In this session we are going to discuss how we can create a mixture model using PyMC3. First of all, I would like to tell you I am copying most of the codes from the PyMC3 documentation because it is very easy for you to access the code and also to understand the things in a better way than we are explained on the basis of our probability concepts. That means you can extend your knowledge by consulting documentation available in PyMC3. The basic idea is that PyMC3 is working as same as a mathematician think. So it is thinking in a different way than a programmer. Okay. So first of all we will revisit what is a mixture model. Mixture model is nothing but a probability distribution that defines combination of different probability distribution with some weightage. This weightage is actually a probability distribution. So it is a weighted sum or weighted average of probability distribution of subsamples. So P of xk is actually a subpopulation distribution. Using this subpopulation distribution we generate a general distribution, more clearly a general probability distribution, and it is known as the mixture model. If this P of xk, each P is the sub probability, P of xk is normal or Gaussian, it is called a Gaussian mixture. If this P of xk is a Dirichlet distribution, then it is called a Dirichlet mixture model. Like that, we can create any type of mixture distribution using this idea. Okay. As the first step in PyMC3, you should install these dependencies. Before that I will explain what is the working concept of PyMC3. I already told you it is work as similar to a mathematician think. For example, consider this distribution P of x comma theta comma n. P of x comma theta comma n is equal to ncx theta raised to x into 1 minus theta raised to n minus x. This is the probability distribution for binomial distribution with probability theta. See, mathematically speaking, to derive the binomial distribution we need this theta. If you have this theta in your hand, you can calculate 1 minus theta, then theta raised to x into 1 minus theta raised to n minus x together construct the distribution part. Then ncx is simply a combination. That ncx is depending on n. N is considered as number of samples we are selecting. So in a practical situation, this n is taken from the context. Suppose we need 1000 samples. In that case we take small n as 1000. Suppose we need 500 or 5 lakhs number of samples. In that case n varies from this 100 to 5 and then 50,000 or 5 lakh, whatever it is. Okay, this is the idea. So you need only theta. That means in order to generate a binomial distribution you need a theta. From where you take theta, depending on that theta, the distribution will vary. That's all. Theta is the probability, it will lies between 0 and 1. That is the idea. Okay. So in PyMC3 we select this theta in one step. Then using this theta we develop second level of distribution. Using that second level of distribution we generate next level of distribution. Like that. This is like a chain. We start from the base, then we mix it appropriately. Whatever you like, in that way we mix it. Okay. Now come into these dependencies. In previous lesson we have already discussed this idea. You should install this set of this combination of libraries. Arvis 0.6.1, PyMC3 3.8, Theano 1.0.4. You just keep this cell as a reference cell. Whenever you are trying to use PyMC3, you copy this cell and paste in the new notebook. This is mandatory because all the combination need not be work in collab. Okay, this is one such good combination. That's all. So all the dependencies were installed. Then we load the necessary libraries. Since we are doing with Collab, we make use of our CPU facility, not using GPU. If you select GPU, there is no change in speed. That is why you insist in CPU version of Theano, because Theano is not that much updated. If you are selecting the GPU version, it need not be work. So convenience, I use this Theano flag device is equal to CPU and float x is float32. We are using these type of tensors to develop our model. Remember, Theano is a high level API that help us to generate tensors, higher level matrices. You think like that. You can store any number of vectors together in a tensor representation. Why we are using tensors? Reason is very simple. In probability distributions, the number of samples may goes to lakhs and lakhs of dimension. In that case, it is not easy to represent using usual arrays or matrices. One such good unit to represent this thing is tensor. That is why we make use of Theano. Definitely you can use TensorFlow, but the TensorFlow compatibility in PyMC3 is not currently available. We are mainly working on Theano background. Okay, so import Theano, then import PyMC3 as PM. So PyMC3 is loaded in terms of PM. Select probability model, that is a simple notation for PM. As we know, the matplotlib is loaded as PLT. The PLT is a short form for plot, like that. This PM is actually a short form for probability model. Then from PyMC3 we import normal, metropolis, sample, MV normal, multi-dimensional normal, Dirichlet density distribution, find map, nuts, that is no U-turn sampling, and slice. All these are available methods. But fortunately we are not using this explicitly in our simple program. This is a usual convention. We load libraries independently. Okay, in from PyMC3 we need not to load everything. We load only necessary methods or libraries or to work with this PyMC3 model that we are discussing in this session. Okay, then import Theano.tensor as TAT. I am using this Theano tensor to make sure that our model will informative. The model will lose much. If our model will lose the information, we cannot get a proper mixture distribution. That means if you are working with clusters, you have to ensure that every cluster should contain at least a minimum number of points. Otherwise, if we are talking about the clustering and clustering algorithms using our soft clustering approach or probabilistic approach, it has no meaning at all. Suppose we develop a model which divide the entire data into 10 or 20 clusters, but unfortunately most of the 10 clusters doesn't contain any point, then that cluster has no meaning at all. The cluster unit has no information it possesses. That is the reason. Okay, for that purpose I am using this tensor operator TT. Another one is from Theano tensor I create this determinant. I need the determinant of a matrix. This linear algebra I am using linear algebra from this tensor Theano.tensor. I am not using linear algebra component from our usual numerical Python or NumPy. Okay, because we are dealing with tensors, we cannot doing with ordinary arrays. NumPy means numerical Python, it working with arrays, but we are taking this determinant for tensors. That is why I choose determinant from Theano.tensor.nlinalg. Then import NumPy as NP. Definitely we need some array operation for loop and also some slicing operation. We need arrays that for that purpose we import NumPy. Again matplotlib .pyplot as PLT. Matplotlib is the main visualization library we are using in Python. I import Seaborn as SNS because I need some upgradation of plots for the purpose of visualization, we need some special type of backgrounds or appearance for actually themes. For these themes I am using SNS. SNS is a seaborn object. Then I am creating a sample data, because the model should be generated with the help of a sample. Our PyMC3 model is a mathematical framework. It will have a live only it has some input data or observed data. The model is a theoretical one. It will active with the help of a sample data. That is why we are generating samples. Here also I am generating a synthetic sample. I am explaining everything in the basis of clustering. That is why I am developing a synthetic data with 3 clusters. See this np.random.seed 1 2 3 4 5. You can choose any number here. It is just for reproducibility in research, because once you run this particular code cell, you get a particular set of samples. The second time it will create a different set of samples, because we are using random numbers and random data distributions from Python libraries. It will varies with time. So a better idea is we are including some random seed along with the cell. It ensures the same result at every time it runs. One interesting question is that if we are putting such a random seed, you got the same result, then where is the randomness? Actually we try to override the randomness just for the purpose of same result, the result consistency in the presentation viewpoint. That's all. Otherwise in first presentation you get one data, then its distribution is somewhat in a particular way. The second time when we run the same program, you get a different output. So naturally there is a question, what happened to this system? This program is consistent like that. But to minimize this dilemma, we try to fix the randomness in such a particular way. We are using the randomness in the case of samples, but we preserve the randomness everywhere at every time. Preservation of randomness, that is a good word. So here I am intending to create a very simple model with the 3 clusters. That is my aim. I am creating 500 data for the entire 3 clusters. Then spread is 5. That spread is defined explicitly to create the centers. I create the centers as the center point of clusters. That is an array with the 3 points minus spread, comma 0, comma spread. So the first point is minus spread. So the first cluster center is minus spread, but spread is 5. So minus 5, 0, 5. So we have 3 clusters. One center is minus 5, and second center is 0, and third center is 5, like that. Now we fix the center. Now we generate data. For that I create a vector v that is equal to np.random integer from 0 to k n data. It creates random numbers within the range 0 to k. That means 0 to 3. But it contains 500 data. That means it creates 500 data ranging from 0 to 3. Then we generate the data. Here we fix the center, fix the number of clusters, and we fix how many points we are going to generate. Then we are going to fix the vector v. That vector v is the random data mixing. Randomize the data. It will not take continuous numbers from 0 to 500. Not like that. It creates random numbers in between 0 and 3. How many? 500. That's all. Now we actually create a cluster. We need a clustering. Clustering means we are going to bring some points centered about minus 5 and centered about second data center 0 and again third one, that is 5. We collect some points, random points, and bring it to near to minus 5. Again some other set of random points and collect it to and fix it near to 0, like that. Collect it in a different way. We bring it into 3 different groups with the center minus 5, 0 and 5. Say this is the simplest trick. Data is equal to centers of v. We create centers of v. That means centers is an array. We create centers of v plus np.random n data. That means we add this random data to these centers. Add these random points to the centers. And therefore what happened? All the points are centered about these centers. the centers will become a central point of clusters. That is a very simple mathematical trick. We add the center value to every numbers randomly. So the random points lie in between, not in between, nearby that centers. That's all. To understand this idea but in a better way, I visualize using a scatter plot. See, look, here we have -5 is here, then 0 is here, and 5 is somewhere here. Now look into this pattern. The first set of points are scattered near this 5, -5. Here this set of points scattered near 0, and the third set of points scattered near 5. So we intentionally creating a cluster with the help of simple mathematics, simple addition, adding points to the cluster centers. So the points will come near the centers. So we have 3 clusters. We can divide it into 3 clusters, but definitely there are some overlapping. If you draw a straight line in between these first and second clusters through 2, some points may be misclassified. That is the problem related to our hard clustering or usual clustering models. All such problems will be eliminated with the help of soft clustering or model-based clustering that we are discussing in mixture model. Okay. And now we are going to count this. To count the data points, we can use histogram. When we use a histogram, the data points are like this: -6 to 8. The points lies between -6 to 8. The maximum points are near to the 0. The 0 occurs near 100 times, like that. And there is -5. -5 lies 80 times within the clusters, and also 4, 5, 6. Almost 6 and 5 is almost near to 65 to 75. Sorry, 75 somewhat. So simply count of these numbers, -6 to, actually this is 7 to 8 values. These are real values. How many times these real values repeated in these clusters? That is the y-axis. So we can visualize that the system using our histogram plot and also for using scatter plot. One point I am going to tell you here is that whenever you have a data, first of all you have to apply an EDA. EDA means exploratory data analysis. Exploratory data analysis will help you to understand a basic characteristics of the data. Here we create a cluster model mathematically. Then we think about the quality of that clusters. Is it possible to cluster into 3 different groups? And we just look into the scatter plot, we got the idea. Then we also look into this histogram. We know how many repetition will happen to these values. This is the basic observation. Whether you are a data analyst or a machine learning scientist, you should know the basic characteristics of the data. So EDA or exploratory data analysis, the first step. I am using this idea always. That is why in all my lab sessions I am using either some histogram or some scatter plot or whatever it is. Most suitable plots we will select in that case. Sometimes a phase select plot, but sometimes we use some ggplot2 library for better classification and grouping. This is the good idea to understand the data. Okay, now we are going to the core part of this. We are going to create a mixture Gaussian model. So keep the idea. We have 3 clusters. We are going to select points points from these 3 clusters, and we are going to develop a general model. Keep first of all, you think you have a set of data. Now this data is distributed into 3 different clusters that we know now. Now we are going to develop a general distribution, that we are going to mixing these clusters. How we will mix the clusters? First of all, you choose the cluster. You should decide the cluster from which cluster you are going to take the point. Okay, so that is a selection process. Then we identify the how much points to be selected, and how in how much points and in what way we are going to mix the points. All these are the basic idea. So you have to fix this cluster and also how the cluster points will be mixed. this will be developed mathematically with the help of this PyMC3 model. So this is the basic definition. The model is a keyword. Model is equal to pm dot model. This is an object from our pm. Pm is as you know, this is a PyMC3 object. Then with model, this is a with function is similar to the functional notation R programming. Whenever we are using a model, then we have to repeat the keyword model everywhere. So one easiest way is you just specify I am fixing this model. That is the keyword with model. Whenever you specify with the model, then all the lines below that with model come under the head model. So this with model means we are doing all these things within this model object. Now we are fixing the cluster size. P is equal to, so we need a P. You think this P as like a theta or a variable, a parameter. Pm dot dirichlet. I am using the same name. Here we need P. I use the same name P here because this function will create an output P. We store the same P here. A is equal to np dot array 1, 1, 1. We need floating values, that is why we put 1 dot, 1 dot, 1 dot. If you discard this point from here, then what happen? It create only integer. But we need continuous values, that means floating values between 0 and 1 here. Remember, Dirichlet distribution is the higher dimension or multi-dimensional beta distribution. I think all of you remember the beta distribution. This is a higher level multi-dimensional beta distribution that decide what should be the value of a parameter once you know the bounds. Here we fix the bound, upper bound is 1. So when we fix the upper bound is 1, that means it start taking value from the least positive value to highest the boundary value, that is 0 to 1. Then shape K. We need 3 clusters, that is why we create a Dirichlet distribution with dimension 3. Once again, I remind you, this P is the parameter. What is P? It's the parameter taken from a Dirichlet distribution. P stands for Dirichlet distribution now. Now we are going to create a P min potential. See, I have written it. Ensure all clusters have some points. We have to ensure that all the clusters should contain a minimum number of points. Otherwise, this clustering algorithm will fail. So we use this TT. The TT is actually our Theano tensor object. The TT dot switch TT dot min P less than 0.1. Actually, this is a standalone line of code that we are using in missing information from model clustering. Sometimes the model clusters will not give us any information, but before taking samples from a distribution, you should ensure that the distribution will represent the entire data. For that purpose, we are using this line of code, that is P underscore min underscore potential, and also there is one more line, order underscore means underscore potential. All these are some measures that we are going to take while PyMC3 models were constructed. You should keep it in mind. Okay, so we create a Dirichlet distribution, then we use this method. It's an assurance method to ensure all the clusters will contain some points. It is very simple. TT dot minimum of P is less than 0.1, then you just assign minus np dot inf, that means minus infinity. If it is greater than 0.1, you just put 0, that's all. Whatever be the value, there is only a partition less than 0.1 and greater than 0.1. It is less than 0.1, you just add minus infinity. If it is greater than 1, then you should add greater than or equal to 0.1, you should add 0. That means that cluster contains at least some points, whatever be the value. Okay. Now this is the cluster centering creation using this PyMC3 model. Means cluster mean is equal to pm dot normal. Means we use the same word here. This is the parameter returned by this function pm dot normal. I store the parameter with the same name without creating much complications. It will reduce the confusion. That is a simple explanation to use the same name here and here. Then mu. because we are going to generate standard normal distribution or a distribution with the center 0. If the center is 0 and variance or standard deviation is 1, it is standard normal distribution. But I am using center 0 but standard deviation is 15. So all these normal clusters are same normal clusters with the same center. That means all the clusters have same shape. 3 small hills, you can think like that. Then the standard deviation is 15, shape is equal to k. That means a normal vector. The shape is equal to k 3, here k is 3. It means it's a standard normal vector. A standard normal vector in which each normal distribution is centered at 0 and standard deviation 15. That means this is same variance model. All the clusters have same variance. That means all of these clusters are same spread. It's like replica photocopies of each other, like that. Then again, to break the symmetry, we have to make the same shape, same symmetrical point structure within the clusters. We using this small function. That is an assurance functions in PyMC3. Now we are going to derive another parameter, standard deviation. That is actually for the global model. Standard deviation is equal to pm dot uniform, so uniform distribution. Using same notation SD here and here also SD. Lower 0, upper 20. That means it creates a uniform distribution with the lower value, that is A is equal to 0 and B is equal to 20, like that. And definitely it gives uniform same probability for standard deviation between 0 and 20. That is the idea of using standard uniform distribution is here. Sometimes instead of this uniform distribution we can use one-sided normal distribution or half normal distribution. That is from 0 to right side. It creates also a very good distribution for standard distribution. One more thing is that the standard deviation of our sample is called standard error. The standard deviation of the sampling distribution is also known as standard error. That is why we use the term measurement error. Okay, it's a statistical terminology we are using in sampling. Now, next step is latent cluster for each observation. We are going to take samples from a distribution and we are going to define a category. In a simple sense, you should understand like this. See, we have to fix the clusters. Each cluster denotes a different category. That means we are going to fix the cluster from which we are going to take the point. That is why we are developing a categorical distribution. Categorical distribution is actually a multi-dimensional binomial distribution. We use pm dot categorical, C capital, then category. Use the same name, that's all. For a categorical distribution, see, it is a extension of binomial distribution. For a binomial distribution, we need only one parameter theta. Instead of that theta, we are using p. From where you get this p? P is from this Dirichlet distribution. This is higher level. In first level, we got p. We use that p here to create a categorical distribution. Okay. This Dirichlet distribution is a beta extension of beta distribution that takes the values between 0 and here the bound is 1. So it defines some measure. Using that probability measure, I am constructing a categorical distribution. That is the idea. Okay. Now one more thing, we define a cluster centers here. Using that cluster center, we are going to define the normal distribution. This is called the mixture normal. Why it is called mixture? I will explain that. Here I am using different words. It has no meaning. You can choose OBS here. Also points here. It may confusion. Look here OBS and here points. So in the first look you have a doubt. What is OBS? What is points? It creates some distribution and store in OBS. That OBS is now assigned to point. That's all. Why we need some additional names or additional variables to store same values? It creates a memory leak. So better to use points here or OBS here. Okay, I use this different term just to explain why we are using the same name here and here. Okay, now we move on to the last point. We are going to a Gaussian mixture. What is this mixture? It's a normal distribution. That means a Gaussian distribution. From where it take the values? It takes mu. It create means. From where we takes the means from a normal distribution. See, this Gaussian mixture is a mixture of normals. with some category values. What is this category value? That is a selection parameter from which cluster I am going to take the points. Okay, this normal distribution mix points from different normal clusters, but that clusters will be defined by this category. Then what is category? Category is a categorical variable. So we are using this categorical distribution to mix this normal distribution. So this is a mixture of normal distribution. Then what is, for any normal distribution, it has two variables, namely mean and variance. Mean is mu, that we got from this means. Means is determined by this categorical distribution. Then one more variable, that is sigma or standard deviation. Then what is data? It creates a normal distribution with the help of our observed data. That is why we use the term observed. It's an indicator. That observed means we are trying to inform the model, see, this is my data. Based on this data, you have to construct a Gaussian mixture. I repeat, see, PyMC3, this is my data, observed is my data. Use this data, you create this model, make it alive with the help of this data. That means that you have a model, I agree, it's a very wonderful model, but you have to create that particular model with this input data. That is the meaning. So it is more logical and more mathematical or probabilistic compared to programming. In programming, we start from some initial step and initialization, some assigning operation, some comparison, and finally we got some result. But it's not like that. Here I have a mathematical idea in my mind. I define all this idea here, and finally I tell this PyMC3 to create a normal distribution with these parameters adjusted to this observed data. Actually, in programming we are doing only with the input data, but in PyMC3 it is the last step. That is, programming happened only at the last step. The remaining ideas are related to purely mathematical or statistical idea. This is the crux of this particular PyMC3 model. Okay, now we form a sample. This is the only step I am going to explain. Then this is the distribution. We got the distribution PyMC3 model. I know the model. Now we are going to create a sample. Sampling can be done in different ways. In last week we have discussed the various algorithms, MCMC, Gibbs sampling, etc. We are using both here. See, I create samples in a complicated structure or in a compound structure. In step 1, I create a metropolis sample. Metropolis means MCMC. Metropolis sampling technique is a special type of MCMC. What are the variables I am going to model here? P, that is P is the probability that captured from our Dirichlet distribution. SD, standard deviation, is captured from our uniform distribution, and means is again taken from the clusters. Clusters means normal distribution. Then second step, that is step 2, PM dot element wise categorical variable is simply category. Category is, the category is a categorical variable. Then it represents the clusters, from which cluster I am going to take the points. That is a mixing. 0, 1, 2. We have 3 clusters. In Python we start counting from 0. Arrays are indexed with 0. That is why 0, 1, 2. You can choose 1, 2, 3, no problem. But this is the correct idea we are using in Python, because in arrays and also in tensors the indexing start from 0. That is why I start with 0, 1 and 2. Then TR is simply a trace. A trace is a sample. That is PM dot sample. How many samples we are generating? 1000 samples with a step. Step means which iterations we are using. We are using 2 sampling algorithms. One is Metropolis or MCMC. Second one is element wise category. It is actually a Gibbs sampling. We are using Metropolis or MCMC and GIMS together. Metropolis and Gibbs. Step is equal to step 1 comma step 2. That is why it is called a compound step. We are using 2 types of sampling here. Tune 5000. We are tuning this 10,000 samples out of 5,000 samples from this 10,000. We have total 10,000 samples we are selecting, but we insist the model that at least 5,000 samples should be matched with this particular distribution. At least 50% or 50-50 configuration. I need at least 50% of the sample should be in tune with this normal mixture model. That is tuning. We can avoid this tuning, there is no problem, but whenever we apply some tuning here, it will increase the number of epochs or number of repetitions in taking samples. See, the metropolis sampling or MCMC is the best fit sampling. If you insist some tuning, it will work more. That means it will take more steps to get best samples out of this particular distribution. Okay. Now it do the job. Then what happened? The two chains. That means step 1 and step 2 is here doing two chain, but in one job. That means we are using CPU. If it is in GPU, this number of jobs may be different. If you have 3 cores or 4 cores, normally there are 4 cores in a good GPU machine, at least 4 cores. In that case, you can specify how many. We can here put comma jobs or some is cores. You can use cores. Cores is equal to 4 or something like that. Then it will work parallelly. We got the result in a fast way. Okay. So the sampling done. It will take some time. Then I trace the sampling distribution. We have to trace it, how it will look like. For that I am using RVis, but here I am not using RVis. The same trace plot from this probability model or PyMC3 model. See, I hide this or comment this line. If you are using plotting this trace TR, if you are using RVis, the name is AZ, use AZ dot plot underscore trace. The same function, trace plot changes to plot underscore trace. But interesting thing is that if you are using PM dot trace plot, it make use of this RVis. RVis is a fundamental plotting tool for random variables. RVis means random variables. So it will create a plot. So this is the plot generated by our PyMC3 model. So this is P. P means our variable taken from the Dirichlet distribution, that is a probability. It will have the shape of normal distribution. See, this is red is expected, that is from the sample. This green is the distribution created by our model. Once again, red is our original data distribution and this green is the distribution created by PyMC3 model. It almost fit. We have 3 clusters, so we have 3 different plots. The left side represents a KDE. I think you may remember that KDE, kernel density estimation. The left side plot is created by kernel density estimation. Right side is actual values, how it varies. It's like a wave. And second one is standard deviation. Remember, we take this standard deviation from uniform distribution, even though it creates almost same distribution for 3 clusters. Then third variable is means. Means we have 3 clusters. Definitely there should have 3 cluster centers. It is normal distribution, so this is the first cluster, second cluster and third cluster. Remember, first cluster is centered about centered about -5, second cluster is centered about 0 and third cluster is centered about 5. Its distribution is showing like this. You can see, you can compare this particular plot with your original scatter plot. In that scatter plot we have 3 distinct distributions. This is actually distribution of means of these 3 different clusters. Then convergence plot, we plot, this is the complete plot. Then we are going to take a portion of the plot after a finite number of iterations. Here we take the samples after 5th iteration. In that case also we should have the same shape. Why we are using this type of strategies in plotting? Idea is very simple. Initially the algorithm is very slow and lazy. Later on the algorithm will work in an improved way. So what is the performance of the algorithm? After certain stage will help you to identify the performance of the algorithm. That is why I am using the plots after certain epochs or certain stages. This is next step is model comparison. In model comparison means how this distribution is. I already told you what is standard deviation, CSD. SD or standard deviation is actually is called sampling error. If the sampling error is much high, then that model is not reliable. How we can assess a model that it should have more reliable? That means its error is minimum. This is the basic idea. So I am taking autocorrelation of the standard deviation. There are two standard deviations, 0 and 1. In 0 standard deviation, the 0 error case, the distribution is like this. See, the horizontal line is 0. This is also known as residual plot. If these errors are come near the 0, it have almost same pattern. That means the model is consistent with the 0 standard deviation and also with the 1 standard deviation. The correlation plot will gives a symmetric curve about this horizontal line, and that means this model is consistent. Then sampling of cluster for individual data points. These are simple plots how the data is distributed among the samples. I am taking about 5000 samples, that is in x-axis. In y-axis how it is plots. It is like in a barcode. Between the first 500 samples, there are more points in the the first cluster. 0th cluster means first cluster, and after in between these 2000 and some 2100 or 2200, there are no sample points in this cluster. How the data points, how the sample data points are lies in particular cluster? It is like a cross section taken from the clusters. Now how the cluster works, that is cluster quality check. I am defining a function cluster posterior. We will discuss this posterior distribution in more detail in next module, that is Bayesian models. Here for your information, what is posterior? We develop a cluster, a mixture model. What you get from mixture model is called the posterior distribution. We have input some basic distribution like Dirichlet, normal, uniform, categorical. Bring all this together, you got a Gaussian mixture. That Gaussian mixture is your posterior. The model, what the distribution from what you get from the model is called the posterior distribution. What this particular function tell is, I put I is equal to 0. That means when we choose the first point, 0th point, then this V of I means V is our cluster center, then V of I, this the cluster V of 0 is the corresponding cluster. See, the true cluster is 2. That means this is cluster 2. Then what is the when I is equal to 0, what is the point? The data value is np dot round data of I. Data is the distribution of data points, then comma 2. We round the point into 2 decimal points. See, 3.29. Then I create a histogram. This defines the axis x max, x min, and also ticks. We need 3 clusters, and so we put 3 cluster marks 0, 1 and 2. Then I plot this function. See, this is true cluster is 3. A data value is 3.29. The probability that the data point is in cluster 2 is very high because this histogram shows the same shape. Okay, out of this 4000 samples will be in second clusters near to 3.29. There are very much low number of points are misclassified into first cluster. That means this model will generate a very good probability distribution function that will separate the points into different clusters. That is why it is called a quality check for the cluster. Okay, whatever we are discussing in mixture model is in the light of model based clustering or soft clustering, because all the effort we are taking here is to explain clustering in a beautiful probabilistic way. That is why we derive all the methods in terms of clustering. So this is a very fundamental, a very basic example of developing a Gaussian mixture model using PyMC3 in cluster viewpoint from a cluster background. Okay, this is all about this session. There is also an assignment for this week. I put a link here. You just click on this link and there is a sample code available. It's a question that is posted in this disclosure of PyMC3. In this discussion, how to tackle this problem. There is a question. There are a lot of answers available in that particular discussion forum. You just go through that discussion forum and sample code, then copy it into a PyMC3 model, then a PyMC3 notebook, especially in Collab, then work around on it, then give a best output from that particular model. You got the complete details in GitHub associated with this link. Actually, this assignment is not to make things difficult, because many of you are not aware of the availability of codes in good positions like GitHub and documentation of PyMC3, etc. While you go through this particular assignment, you are supposed to visit many websites and many GitHubs to collect information or some solutions or better workarounds to solve this problem. So this is the way in which we develop our coding skill. We won't have all materials within our hand initially, but when you try to search new things in new area, you will automatically learn new things. That new things are the spark to do some more advanced things. So new things and advanced things are based on these sparks. Okay, definitely many of you have aroused wonderful doubts related to coding session, but I prepared all the lessons in such a way that initially I have to fill the gap between the pure mathematical background and also with a programming style. That is why I explain all the algorithms in a loosey English style with some examples and analogies. But in the last discussion, some of you point out that we expect some additional things like interpreting mathematics programmatically, but we have already fixed everything. That is why we supplement some additional discussions on coding. This is the way in which we transcend mathematics into programming. There is also some wonderful examples of multidimensional Gaussian. I copy this from PyMC3 documentation, but it's a very nice one. It's straightforward. That is why I'm not explaining this. Here we create a mixture directly with a single sentence. We likelihood function is equal to pm.mixture. That's all. It creates a mixture model. There is also weight W, that is a Dirichlet distribution. It is more close to our mathematical definition, but it will not work better in clustering. That is why I first explain the clustering model, but this is a good try how the multinomial Gaussian is generated with the help of PyMC3 in few line of code, 1, 2, 3. That's all. We create 3 line of code. It creates a multinomial Gaussian distribution. Instead of this normal distribution, here this PM is equal to normal distribution, we can use Dirichlet distribution. In that case, it automatically becomes a Dirichlet mixture distribution. So the idea is that the components are normal, this mixture becomes normal mixture. The components are Dirichlet, it automatically changed to Dirichlet mixture. That's all. That much simple changes happened in this PyMC3. So PyMC3 is very good in programming. It will reduce all the efforts in probabilistic programming into few line of copy paste codes. That's all. So this is all about the discussion on this mixture model programming. Okay, have you a wonderful time. Thank you very much.